All right, so we're going to start this quarter talking about simple harmonic motion. And I've uploaded a set of notes that you should feel free to follow along with. I strongly recommend you make your own notes by either adding to these or starting a totally new set. It will help you to learn the material much better. Now, the first page is really just review. This is how Hooke's law works. The second page is where we start to get into new things. In this video, I want to focus on the differential equations. Those are the scary parts usually for people. If you haven't taken differential equations, or even if you have, it can be a bit overwhelming. The way physicists do these is we look for a pattern, we look for our equations to match something we've seen before, and then we make what we have look like that thing we already know, and then we apply the pattern. So the differential equation we're dealing with here is a classic one, and the one that we know has the form second derivative is proportional to negative the original function. And so we end up with this exact thing here with the case of a spring, a Hookean spring, one that follows Hooke's law. Now there are several things we have to do in order to nail down the details of the solution to this differential equation. So first we have to figure out what functions would fit that pattern. In this case, a sine function fits, so does a cosine function. The nice thing is that those two are actually kind of the same function. You can see this if you look at a graph. They look the same, just one is a little to the side of the other. And what that means is if we input a little shift in the horizontal variable, in this case time, then we can change a cosine into a sine, or we could change a sine into a cosine. So what we're going to do is just choose one. In the notes here, I have chosen cosine. And we're going to input some shift with our time variable. We don't know yet how big that shift is, but we'll solve for it. And here I've called that phi. And that the words, the name for that are the phase constant. Now be very careful. You always want phi to be in radians here. Okay? Now other arbitrary constants that we have an A that stands for amplitude, and we have an omega, which stands for angular frequency, which was discussed last quarter a little bit, but not really. Where you've seen omega before was angular velocity, which was the radians per second that an object covered as it moved around a circle. But if you think about circles as being cycles, then you can see this is kind of the same thing. So once around a circle would be one cycle of a continuous motion like this, right? So the number of times you go around the circle every second, that would be your frequency in hertz. So the number of radians that you go around every second, that's your angular frequency in radians per second. Okay? Now here, we're going to switch the name between angular velocity and angular frequency, but really fundamentally they are the same thing. Now, that means that we have three constants, and we need to solve for those three. And generally speaking, the first thing you do is you take your function. In this case, we've got x is equal to a cosine of omega t plus phi. You take derivatives of it, you plug it back into the original differential equation. Okay? You do whatever you can do. Cancel things, simplify things, whatever, and see what's left. So if we do that, we can see that omega would have to be the square root of k over m. That it has to be like that, or else the equation isn't true anymore. So we've already got one of our arbitrary constants done. Okay. Now, a and phi those are going to depend on something we call initial conditions. In other words, what is the position at the beginning? And what is the velocity at the beginning? By knowing those two things, again, you can plug your information into the function, like x at time 0 would be cosine times a of 0 plus phi. And then v at time 0, well, let's see, that would give us a negative omega a times sine of 0 plus phi. So we have two equations, two unknowns. You've got some practice now in solving systems of equations like that. Generally, we do it through substitution. And you can find a and phi. Now, even if you use the same spring and mass, depending on how you start the motion, a and phi could be different in different situations, which is why there isn't a way to just say, well, for example, a is k squared plus 3 or something. I mean, there is no such way of finding it. You're going to have to do the substitution, the solving the system of equations. Now, this can be a little tedious when you first do it, but as you get used to it, it's going to go faster and faster. Now, the rest of this set of notes pretty much deals with those concepts, looking at it from a graphical point of view, looking at it from a pure algebra point of view, doing it for different situations. Now, let's see, 12, 13, there's about 13 pages just to that section. And then we get to pendula. I'm going to make a separate video for those because those are the focus of your labs in this section. All right, so that's it for this first video, just focusing on the differential equations and what you do with them.